Before we will go on with the next distribution, I'll try to explain you in a few words a concept of a Poisson series of events. Actually, not our science, not the probability theory, but the theory of stochastic processes deals with this series of events. But still, it's better for you to know what it is. So let's suppose that there is an event of interest, not a random event, just an event, and these events happen, and the time between their happenings, between their occurrences, is random. For example, you are listening for my lecture, and the event of interest is me saying some words, let's say word so. So you can see that, oh, he said so, then in 33 seconds he said so one more time, then in 1 minute and 2 seconds he said so one more time, and so on. Or, for example, you open the window and you look at the street, and the event of interest is a person passing by your window. And so you can also see that times are random. So the one person passed, then in several seconds the other one, then in several seconds the other one, and time you are waiting for the next person to pass is random. This is called series of events. And so to be called Poisson series of events, series is to meet 3 conditions. And to be called not just the series of events, but Poisson series of events, a series is to meet 3 conditions. So what is an intensity of a series of events? Intensity is an average number of events that happen in a unit of time. For example, if your unit of time is 1 hour, so intensity of a series is how many events happen on average in 1 hour. If your unit of time is minute, so then intensity of your series is how many events happen on average in 1 minute. So a series of events is called a Poisson series if it meets 3 conditions. The first condition is constant intensity, so that intensity doesn't change. For example, if in the beginning of my lecture I pronounce the word so on average 3 times in a minute, and by the end of the lecture I do it on average 10 times in a minute, so this means that intensity is not constant. So, but it must be constant for our series to be a Poisson series. Then, the second condition is that times, so moments, where the events of our series will happen in future, must not depend on the moments where these events happened in the past. The second condition is that moments of future events of our series must not depend on the moments of the previous events. So the future does not depend on the past. It depends only on what is happening just now, not on what have already happened. So the third condition is probably the most difficult to explain, but let me say so. If you have an interval of a time interval of a given length, let's say delta t, and this length tends to 0, so delta t tends to 0, then probability that at least one event of our series will happen during this interval tends to 0 with the same speed. Or in terms of calculus, we can say that they are infinitesimals of the same order, delta t and probability that at least one event will happen during this period. So, if an event, so if a series of events meets these three conditions, it is called a Poisson series of events. So how this concept of Poisson series can be applied to our real life? It was discovered that this model is very good to describe what we call queuing systems. So queuing system is, for example, a shop where customers come and buy something and so leave the shop, or a call center where people call to the call center to ask some question, and after getting an answer, they just quit this system. So systems of this kind are called queuing systems. And series of customers go into the queuing system, entering this system to get some service, is a Poisson series. And series of customers that go out of this system after they got what they needed is also a Poisson series. The only one thing is that we are to consider such a system in such a time interval that intensity of a series is constant. So, for example, if we consider a shop that is working 24 hours a day, for example, we should consider the work of this shop not during the whole day, but from, let's say, during the peak hours, from, let's say, 5 p.m. to 8 p.m. And inside this time interval, we can imagine that the intensity is almost constant. So this mathematical model is used to describe, to model, for mathematical modeling, for computer modeling of queuing systems. And there are two distributions based on this concept of Poisson series of events. The first one is Poisson distribution. So this is a distribution of a random number of events from a Poisson series of events that happen in a time interval of a given length. So if you know the length of the time interval, and it is capital T, and if you know the intensity of the series, and it is lambda, then number of events, random number of events happening during this interval T has Poisson distribution with parameter A equal to lambda times T. So the symbol for Poisson distribution is, the most common symbol is first 4 letters of the Poisson's name, or in some textbooks they prefer capital Greek letter pi as a symbol for Poisson distribution. The PMF, so probability to take a particular value k, is equal to a power k divided by k factorial times e to the power of minus a, and both expected value and variance are equal just to a in this case. Let's solve an example. There is a town, and probability that no one in this town will call emergency service during 1 hour is equal to 0.05. And they ask to find average number of calls in 1 hour and probability that no more than 3 people will call the emergency service in the following hour. So, actually, what is the random variable of our interest here? So, what is the random variable we are talking about? This is the random variable is the number of calls the emergency service receives during 1 hour. So, x, the random variable of our interest, is the number of calls. Number of calls in 1 hour. What is given? They say that probability that no one will call in 1 hour is 0.05. What does it mean, no one will call? So this means that x is equal to 0. So number of calls in 1 hour is 0. Nobody called. So they gave us that probability that x is equal to 0 is 0.05. And what do they ask? They say, so what is the average number of calls they receive in 1 hour? So average means mean, means expected value. So they are asking for the expected value of x. And then what is the probability that no more than 3 people will call in the following hour? So probability that x, number of calls during the next hour, will be no more than 3. So this is given, and we are to find these two. As for the distribution, nothing is said about the distribution, so like we don't know. But in such a situation, when the random variable of our interest is a number of customers that want something from some queuing system, and the call center of the emergency service is a classical example of a queuing system. So we can assume that x follows the Poisson distribution. So in problem books, in exams and so on, tests, they usually tell you that let's assume that x has Poisson distribution, or you can assume, or it is given, or something like this. So usually they tell you that the distribution is a Poisson distribution. But even if it is not given, you can assume this as you're dealing with a queuing system. So let us do so. Let us say that let's assume that x follows Poisson distribution, and the parameter is yet unknown. So the first step before we can answer these questions is to find the parameter. To find the parameter, we are to know the formula for the probability. So we are given that probability that x is equal to 0 is 0.05. So we need to know the general formula for the probabilities of this kind. So the general formula is, let me remind you, so probability that x will take value k is a to the power of k divided by k factorial times e to the power of minus a. In our case, a is unknown and k is equal to 0. So, probability that x is 0 is a to the power of 0 divided by 0 factorial times e to the power of minus a. So a power 0 is 1. 0 factorial is also 1 by definition. So 0 factorial is defined as 1. And so we have only e to the power of minus a left. And it is equal to 0.05. So to find e, to solve this equation for a, to find a, we need to take logarithm of both parts of this equation. So logarithm of natural logarithm of e to the power of minus a is equal to logarithm of 0.05. This is minus a. As logarithm and exponent delete each other, and logarithm of 0.05 is approximately minus 3. So a is approximately 3. So now we can answer the first question, as we know that for Poisson distributed random variables, expected value is equal to a, equal to the parameter. So this is 3. So average number of calls they receive each hour is 3. And as for the second question, we need to apply this formula. Let me free a little bit space for myself here. Probability that x is less or equal than 3 is probability that x is 0 plus probability that x is 1 plus probability that x is 2 plus probability that x is 3. So sum of 4 probabilities, and all of them can be found with this formula. So we know a is 3. We know e to the e power minus a, that is 0.05. And so we are to substitute different values for k, 0, 1, 2, and 3. So let's do this. So 3 power 0 divided by 0 factorial times e to the power of minus a is 0.05. I'll use this equality. So plus 3 power 1 divided by 1 factorial times 0.05 plus 3 power 2 divided by 2 factorial times 0.05 plus 3 power 3 divided by 3 factorial times 0.05. So this is 0.05, and here I have 1 plus 3 divided by 1, 3, plus 3 squared, that is 9, divided by 2 factorial, that is 2, 9 over 2, that is 4.5, and here 3 cubed, that is 27 27 divided by 3 factorial, that is also 9 over 2, by the way. So 3 is cancelled, and we have 3 squared over 2, so plus 4.5. Finally, we have 0.65. So, probability that number of calls will be less than average, less than the expected value, no more, not less, less or equal, no more than the expected value is 0.65. So, in other words, we can say that if we divide the working time of this emergency service into hours, approximately 75% of all hours will be such hours that the number of calls is no more than 3. That is the meaning of this probability. The second distribution, based on the concept of a Poisson series of events, is an exponential distribution. Usually we say that a random variable has an exponential distribution with parameter lambda if it is equal to the time of waiting for the next event of the Poisson series of events. So time we will wait for the next customer in a shop, for the next call in a call center, is an exponentially distributed random variable. The symbol for exponential distributions is letters EXP, and 3 distributions we have already discussed were all discrete distributions, and this is a continuous distribution. So time of waiting for something is a continuously distributed random variable. So that is why here we don't have PMF, but we have PDF, probability density function. So you can see formulas for the PDF, small f, for the CDF, capital F, and for expected value and the variance. They are equal to 1 over lambda and 1 over lambda squared respectively. And now let's study one interesting property, interesting feature of the exponential distribution. Let's prove the following proposition or following theorem. If x has exponential distribution with some parameter lambda, then probability that x is more than t plus tau, given that x is more than tau, is equal to the probability that x is more than t. So, what is this? What's the meaning of this equality? So, x, by its physical meaning, is the waiting time for the next event in a Poisson series of events. For example, x is a waiting time for the next customer at your shop. So it's how long you will wait for the next customer. This is probability that you will wait more than t minutes. And this is probability that you will wait more than t minutes after you have already waited for tau minutes. So this is a conditional probability given that you have already waited for this time you have already waited for tau minutes, your waiting time is already more than tau, and this is probability that you will wait for t minutes more, so that your waiting time will be more than t plus tau. Tau is the time you have already spent waiting. So this means that probability that you will wait for t minutes is the same as the probability that you will wait for t minutes after you have already waited for tau minutes. So this equality describes this property of Poisson series of events. I have explained to you that future does not depend on the past. So this information that we have already waited for tau minutes doesn't change anything. So it's no matter, have we already waited for tau minutes or not, probability to wait for t minutes more is the same. So let's prove this equality. Let's consider this probability. This is a conditional probability. For conditional probabilities, we have a formula that probability of A given B is probability of A intersection B divided by the probability of B. So let me apply this formula for this probability. So probability that x is more than t plus tau, given that x is more than tau, is, according to this formula, probability that x is more than t plus tau, and I use this sign instead of intersection, so given, no, not given, but at the same time, so x is more than tau divided by the probability that x is more than tau. So this is the probability that at the same time this and these two events will happen at the same time. But you see that actually this is a subset of this. So if you are waiting for t plus tau minutes, if you are already waiting for t plus tau minutes, so this means that you have already waited for tau minutes. So if this is true automatically. That is why probability of the intersection of these two events is equal to the probability of the first one. So because this implies this. So if this is true, this is automatically also true. So that is why this event simply disappears, and this probability is equal just to the probability of the first one. So probability that x is more than t plus tau divided by the probability that x is more than tau. So I say that this is equal to 1 minus probability of the complement event, probability that x is less or equal than t plus tau, divided by I do the same operation in denominator, so 1 minus probability that x is less or equal than tau. So, and then I say that actually what I see here reminds me the definition of the CDF. So let me remind you here. So CDF of a random variable is probability that x is less or equal than small x. So I see here that probability that my random variable is less or equal than something. So less or equal than something, this means that this is the value of its CDF in this point. So I say that this is 1 minus CDF of t plus tau, and here 1 minus the CDF of tau. And then I should know how the CDF of the exponentially distributed random variable looks like. So the CDF in case of exponential distribution is 0 for negative axis and 1 minus e to the power of minus lambda x for positive axis. So I substitute this formula here for f, and I get 1 minus e to the power of minus lambda times t plus tau, and here 1 minus e to the power of minus lambda times tau. So these ones are cancelled, and so here I have e to the power of minus lambda t minus lambda tau, and here e to the power of minus lambda tau. And so this is cancelled also. So this is cancelled with this, and what is left is just e to the power of minus lambda tau. And now I do the operations I have already done, but not from the left to the right, but from the right to the left. So I say that this is 1 minus e to the power of minus lambda tau. Then I say that this is f of tau, of t, I'm sorry. So 1 minus f of t. This is 1 minus probability that x is less or equal than t. And this is probability. Sorry, this is probability that x is more than t. So the equality is proved. So I started with this and I ended with this. So exponential distribution is such a distribution that if we describe it in time, in terms of waiting time, in terms of time we spend waiting for something, so it's such a distribution that probability to wait for t minutes more, or t hours, or t seconds, it doesn't matter. So probability to wait for t minutes more after we have already waited for some period is the same as just probability to wait for t minutes. So information about the past does not affect the future. So we know something about the past, we know something about what have already happened, but it doesn't change any probabilities of the future events. That is the Poisson Poisson series of events.